Today, I'm going to focus on one particular topic in machine learning, that is learning with unpaired data. First, I want to spend like 1 minute to introduce my research areas. Basically, I have two main research areas, computer vision and data mining. In computer vision, we try to make computers see. So I work on problems such as visual recognition using less or weakly labeled image data, medical image video analysis, vision plus language, and image video synthesis. In data mining, we try to let data speak. So I work on topics such as computational social science, data analytics for healthcare and wellness, urban computing, affect analysis, and deep user profiling. Even though it looks like I have two separate areas, but they have much in common. So as input, we frequently rely on big data. And as tools, we always rely on machine learning. As we all know, machine learning, and in particular, deep learning, has made great advances in recent years. And we also know that these recent successes by deep learning have largely been driven by big data, and in particular, annotated big data. So do we need better algorithms, or do we need more data? So here's a quote from Peter Novick. He says, more data beats clever algorithms, but better data beats more data. So the hope for many of us is whether we can build good machine learning algorithms with small data or less data. So let's look at this spectrum of machine learning. On one extreme, we have supervised learning. Supervised learning tend to give us the highest accuracy, but with a high cost. At the other end of the spectrum, we have unsupervised learning. Okay, let me get the laser pointer working. Okay, we have unsupervised learning, which would incur low cost, but usually doesn't work as well as supervised learning. In order to strike a trade-off between cost and performance, the cost would include, delay, money, manpower, data annotation, so on and so forth. We have other options between the two extremes. Naturally, we have semi-supervised learning, but recently, two areas that can potentially deliver better or higher trade-off are the following. One is learning from noisy labels. The other one is few-shot learning. But today, I won't talk about those two. Instead, I'm going to focus on this particular area of learning from unpaired data. I actually position it more towards unsupervised learning because it typically incurs the lowest cost, only slightly more than unsupervised learning. Okay. All right, let's first look at a few motivating examples for learning with unpaired data. In machine learning, our goal typically is to find a mapping from an input to a structured output. Okay, so in machine translation, we would want to take a sentence in French and translate into English, right? In image style transfer, we may want to repaint a horse to make it look like a zebra. In image captioning, our goal is to generate a sentence that would describe the content of the image. We have other applications for machine learning of this nature as well. In image enhancement, we may want to take a underexposed image and make it properly exposed. And in image dehazing, we want to take these images taken under hazy conditions and make them look clear, okay? And finally, in medical applications, we may want to take CT images with artifacts. The artifacts can be caused by metal implants in the patients. And we want to not only remove the metal implants, but more importantly, remove the artifacts caused by the metal implants. So there are quite a few, or we can say a wider array of applications where typically we would require paired training data, right? We need to know the input. We also need to know the target output so that we can find a good mapping. However, in the 6 scenarios I just mentioned, if we look closely, we'll discover that in some cases, collecting pair data is expensive. In some other cases, collecting pair data is impossible. Okay, for machine translation, certainly it's possible to collect pair data, right? You get a sentence in French, a sentence in English, and that's a pair data, right? The only issue is we need people who are specialized in both languages to provide the pair data. In image style transfer, let's say from horse to zebra, actually it's impossible to collect pair data because we don't have horses with zebra texture, right? In image captioning, again, it's possible to collect pair data, right? You get an image, you ask someone to write a sentence about the image content, but usually that's expensive. In image enhancement, if we try to improve the quality of low light images, it's possible to collect pair data. However, it's actually quite expensive. So I have $2 sign there. Why is it more expensive? Because you would have to take a pair of images, one with underexposed setting and another one with proper exposure setting, right? So you need to align them, make sure they are about the same image. So that can be expensive. In image dehazing, it's actually not clear whether you can actually find paired data, because ideally you would need to take a picture of a scene under clear sky, and then you wait for a few days when the haze comes, and you take another picture of exactly the same scene under hazy conditions. That can be very, very expensive. Finally, in medical application, I mentioned, when we try to remove the artifacts caused by metal implants, it's also questionable whether you can find paired data, because you would need to have the foresight to take picture of the patient before the metal implant and after the metal implant. That's actually quite difficult. And if it's possible, it's very, very expensive. All right. So given all these issues, we want to explore a scenario where we don't need to collect paired data, okay? Because unpaired data are much easier to collect, right? So the hope is we formulate a learning problem with unpaired data such that we either don't need any annotated data, or we need a very little lightweight annotation, right? Let's say for machine translation, we can find articles in English, right? From New York Times, Wall Street. And on the other hand, we can find news articles in German. Actually, I can't pronounce this uh, newspaper because I don't understand German. Okay, but it shouldn't be too hard to collect articles from newspapers in different languages. Okay. All right. So we can get unpaired data. That's no problem. The problem is we still need some kind of alignment. Okay. That's actually the key to unpaired data learning. Okay. So typically, how do we establish some kind of alignment? We rely on two major types of losses. One is a reconstruction loss. I'll explain that in detail soon. The other one is GAN loss. Okay. With these two losses, we can go from one domain to another and then come back. Okay. And formulate a manageable problem for learning with unpaired data. All right. So in the next half an hour or so, I'll dive into some details in these 5 example problems to give you some idea how we can deal with learning with unpaired data. Okay, let's start with machine translation. Okay, the current mainstream approach in machine translation is called neural machine translation, driven by deep neural networks, right? So in this 2017 paper, they proposed a very good scheme. Okay, this scheme would contain several key elements. First, they use a dual structure, which means the same model is used to translate languages in both directions, say English to German and German to English. Okay, so same structure for both directions. Second, they also use a shared encoder, which means the language model is the same for both languages. Okay, so this universal encoder is used to produce a language-independent representation of the input. Okay, and then the decoder can then take this representation and transform into the corresponding target language. Okay, all right. So finally, there's one more detail. They use fixed embedding in the encoder. Okay, the idea is instead of randomly initializing the representation, they use pre-trained cross-lingual embedding model. The effect is the model already is given language-independent word-level representations. So the only thing it needs to do is to build representations for larger phrases. Okay, this is how their scheme works. Basically, decoder-encoder pairs are used to operate on both languages. And this is a typical sequence-to-sequence model. So these blue boxes are models trained in a previous iteration. Basically, they are used as the model for the other language. So you start from one language, use the model of the other language, you go through the encoder and get the output. But you don't have to stop there. You can take another decoder and so it can come back to the same domain. And the intuitions, once you reconstruct this sentence, it should look as similar to the where you start as possible. And you can do it in both directions, right? You have 2 languages. You can do it this way and that way, okay? So this is a very nice framework. And these terms in the green ellipses, they are basically the loss functions. All right, let's look at their results. This is just blue scores on a particular data set called News Test 2014. Okay, so they compared three schemes: unsupervised schemes, supervised scheme, and semi-supervised schemes. I want to draw your attention to this line. Okay, with the back translation pass, they were able to achieve very decent accuracy for many language pairs, and these are comparable to are quite competitive with the supervised schemes. And actually, they outperform the supervised schemes with less data, right? So this is 10K, 100K, and even more. So the unsupervised scheme can outperform even supervised schemes with 100K samples. And they went on to also combine the unsupervised learning with supervised learning and achieve even better results. Okay, all right, so that's an example in NLP. Let me switch gear to computer vision. This CycleGAN work was also published in 2017. It's a very influential scheme. So basically, what they try to address is image style transfer, either from painting to photo or photo to painting, or from one animal to another, or backwards, okay? Or images of one season to another season, okay? So this is a very interesting problem, okay? But the issue is it's nearly impossible to collect paired images in some cases. Okay, the seasons is possible, even though, like I said before, it's going to be very expensive. You have to go to Yosemite twice, one in the spring, one in the winter, one in the summers, in order to get these paired images, right? For Monet painting to photo, well, we don't have pairs. For these, for the animal transfer, we don't have pairs, okay? So how do we solve this problem? This problem is solved by a CycleGAN scheme. Basically, we have one domain, X, and the other domain, Y, right? So we have a generator G that would take X and create something that looks like Y. Okay, we can also consider the problem backwards. We can start with Y and use another generator F to go to domain X. So we have two generators, and we also have two discriminators. Each is used to make sure that the generator output looks similar or indistinguishable to samples in the target domain, okay? But just using the typical GAN, the discriminator generator pair cannot guarantee good results. So these authors propose this CycleGAN scheme. So basically, you start from X, you apply G, get Y hat, and then you apply S to go back to X to get X hat. Similarly, you can start from Y and go back to Y again, right? Either way, this way it's called forward transfer. This one is called backward transfer. But in either case, we can impose something called a cycle consistency loss. In other words, when you get back to the same domain, this output should look like the input. Okay, so this is the forward cycle consistency loss, and this is the backward cycle consistency loss. So they put all this together, they were able to get good results. Let me just quickly go through some of the details. So in the CycleGAN scheme, there are two types of losses. One is adversarial loss. That's standard for GAN. Okay, so you have a generator, discriminator. You go from X to Y, and you want to make sure you satisfy or you minimize the adversarial loss. And you can have the same thing for the backward transform. But the real innovation of CycleGAN is this cycle consistency loss term. So when you go through one cycle forward or goes through one cycle backward, you have losses, right? And you want to minimize them. So the full objective would be the sum of all the loss terms, okay? All right, so let's look at some of the results. Uh, this problem is between an input image and its segmentation map, okay? So if you use a cycle alone, you get something like this. If you use GAN alone, you get something like this. And if you put a GAN forward consistency loss together, it's a little bit better. If you put GAN and backward loss together, you get something like this, right? All right, this is the full result using cycle GAN. And in comparison with the ground truth, we would agree that cycle GAN tend to offer, tend to produce the best results among all the combinations. It doesn't matter whether you want to go from input to a segmentation map, or you want to go from a segmentation map to a scene that satisfies the segmentation map. Okay. All right. So next, I'm going to use one of our papers to illustrate how to train proper machine learning engines with unpaired data. And the problem we deal with here is image captioning. So image captioning is an important task for combining NLP and computer vision. There are a number of scenarios that we can accomplish image captioning. The first one is supervised. That's what most work falls into, okay? So you have a training data set and you have image caption, you have all pairs. And you build a supervised learning scheme so that in the future, given an image, a proper caption can be produced. Okay, so this is the most common scenario. The second scenario is we have some paired data. However, we want to deal with novel objects, right? Objects that have never been mentioned in the training set. So this is the second scenario, okay? How do we incrementally learn to incorporate new objects? The third scenario, C, is domain adaptation. So let's say you have training data set, MS COCO, okay? But now you want to generate captions for medical images. So that will be a totally different domain. So you want to take what you learn in one domain and transfer the learning to the other domain, okay? The fourth scenario is called pivot, okay? Basically, we have paired data between images and captions in one language, but we want to build models for a different language. So you use a intermediate language as the pivot in order to enable or facilitate the learning, okay? The fifth scenario is semi-supervised learning. Basically, we have some pairs and we have some unpaired data, like an independent corpus. So how do we make use of this unpaired data set in order to improve the performance that's obtained on supervised learning, okay? But none of these is what I'm going to talk about. What I'm going to talk about is this last scenario where we have completely unpaired data. We have some images and we have a corpus of image captions. They are not related. Can we still build a decent image captioning model for that? Okay, and that's the work published last year in CVPR. So here's the model we have for unsupervised image captioning. So there are three components. The first component is the image encoder. You have to have that. And the second one is the sentence generator, which is used to generate captions. the third component is the sentence discriminator. Okay, because we don't have paired data, we cannot use supervised learning to build image captioning models. So instead, we use reinforcement learning. Okay, in reinforcement learning, we need some rewards. So here we construct 3 types of reward. The first reward is a adversarial reward. Okay, basically it would come from the discriminator. Okay, because the generated sentence must look like an image caption. Okay, so that's the first reward. The second reward is concept reward, which is to say, if a generated caption contains the concepts that can be detected, like the bench, people, bicycle, in the image, then we'll assign an award. Okay, so we have 2 rewards already, but just having these 2 rewards cannot guarantee we get good results. We need one more types of reward, and that is reconstruction reward. So starting from an image, we can generate a caption. The caption is supposed to describe the image content. So if we can convert the caption back to the image features, they should match the image features very well. Okay, so to make that happen, we actually make use of the sentence discriminator again. We just add one more layer, like a fully convoluted layer, and then that would allow us to project the language features back to the image space, and then we use MSE to measure the loss, reconstruction loss, image reconstruction loss. Okay. Similarly, we can construct sentence reconstruction loss. Basically, you start from a sentence, you go through the image, which is the generator, and then you go back to the sentence domain again. And here we use cross entropy to measure the loss. Okay, putting these 3 together, we can conduct unsupervised image captioning. Okay, let me say a little bit about the data we have. So images are from the MS COCO dataset, and then we crawl from the internet. Actually, we crawl from this thing called Shutterstock. They have images with caption-like descriptions. Okay, so we get 2 million natural sentences from the Shutterstock. Basically, these sentences, we know they describe image content. Okay, so that's the unpaired data set to go with the MS Code data. Okay, so we don't use the captions provided by the MS COCO. Okay, as a bridge, remember we have a reward that's related to concepts in the image. So we use object detectors trained on the open image dataset to detect the concepts in the image. For example, man, dog, cat, so on and so forth. Okay, all right. So here are the results we obtain. Basically, the lower half is the aberration study, where we compare the effect of various components in our scheme, right? So con to sen is concept to sentence, feed to sen is feature to sentence. This is the adversarial loss plus concept, adversarial loss plus concept plus image. Okay, and at the top half, we compared our unsupervised captioning scheme with or without initialization. What do I mean by with initialization? With what I meant is basically we use a feature to sentence model as the initialization for the unsupervised learning part. Okay, so that would give us some gain. Okay, compared with without initialization. This BRNN is one of the supervised scheme. So it does better than unsupervised scheme, but not much better. Okay, I would admit BRNN is not the state of art. It's just a reasonable benchmark we use to compare the performance. Okay. All right. Next, I'm going to give you some qualitative results so you can appreciate the effect of unsupervised image captioning. So these are from various ablation study. BRNN again is from a supervised scheme. For this image, it says a boat floating on top of a body of water. And our scheme actually says a boat is docked in a harbor. Okay. Most people would agree that our result is better. It's better writing. Okay. Why is that the case? Well, BRNN is trained entirely on MS COCO. And MS COCO was annotated by Amazon Mechanical Turkers. They are not necessarily the best writers in the world. While our system, even though it is unsupervised scheme, it actually learned from the corpus from Shutterstock. Uh, Typically, the descriptions were written by the photographer themselves. Therefore, the writing, the level, the quality of writing is better. Okay, and it is reflected in the results of our system. Okay, in this other example, BRNN says a man standing on top of a sandy beach. Okay, well, there are more than one man. Okay, so our scheme actually says a group of people surfing on a wave. Okay. All right. So I've covered a few use cases already. I'm going to continue with two more case studies. Okay. This one is about image dehazing. Okay. In image dehazing, most people use uh, paired data to train models. However, we know we can rely on our external knowledge about the atmosphere scattering. Okay, basically, model says the observed hazy image I is the sum of the following. J is the scene radiance, haze-free image. T is the media transmission map. A is the global atmospheric light. Okay, this is physics. Okay, uh, and our goal is given this one only, Ix. We try to recover the scene radiance, the transmission, and the global atmospheric light. And this was published in a 2018 paper by my group. Okay, so like I said, in image dehazing, many people use synthetic hazy image pairs because they don't really have pairs. So they can create synthetic hazy image pairs by taking a clear picture, apply the physics model to create a hazy image. And then now you have pairs and you can do your normal end-to-end deep learning, okay? However, in contrast, our goal was different. Our goal was to generate realistic haze-free images using only unpaired supervision. Um, okay, what do I mean by that? So I have a pool of hazy images, and I have a pool of haze-free images. They are not paired. Okay, they don't even correspond to the same scenes. Okay. However, given the physical model I just mentioned, our goal is to take one input image, which is hazy, and we use three generators, GJ, GA, GT, to generate three components. The first component is the scene radiance. The second component is the transmission video transmission. And then the third component is the global light, okay? So we rely on these to help us disentangle the image into three components. Of course, if we were successful, then the output of GJ would be the output that we want, which is the haze-free image, right? So why do we need these haze-free images? These are used to construct a GAN loss to measure the quality of the synthetic scene radiance. Okay, that's the use of haze-free image, even though they are not paired. Okay, and then we have an L1 loss between the the haze-free image and the hazy image. Okay. So in our work, we use two types of data sets. One is synthetic data sets like everybody else, okay? There are two of them, the hazy and NYU depth data set. We need the depth in order to account for the effect of depth, okay? But this is where our innovation comes. We actually collect some real image data sets, some hazy, some not hazy, okay? And we have, the only annotation we have is hazy or not hazy, okay? And these are the actual numbers of samples we have. So first, let me show you some quantitative results. So these are various baselines, including CycleGAN. You can certainly use CycleGAN to dehaze, right? You can start from a hazy image, make it a haze-free, and add haze back, and then you want to make sure that the difference is small, and you can do it in both directions, right? So this is CycleGAN, and CycleGAN, in fact, is almost the best among all the prior art. These are the numbers by our scheme, okay? We have three metrics, PSNR, SSIM, and CIED 2000. CIED 2000 is a CIE standard for measuring color difference, okay? And there's some work called DehazeNet, which is designed specifically for dehazing, okay? Oh, by the way, for CIED color difference, the lower the number, the better, okay? And the other two, the higher, the better, okay? Sorry. Okay, let me also offer some qualitative comparison. So these are just some hazy images, and these are the results by various dehazing algorithms. And this last column is our result. This is CycleGAN, this is DehazeNet. So if you compare some of the results, let's say between CycleGAN and ours, we would argue that, this part, this is the artifact, okay? There's no sky, there's no cloud here, okay? And then for DehazeNet, between this pair, I think people would agree that DehazeNet did not completely take out the haze. The image still looks somewhat hazy, okay? All right. Okay, I'm doing well on time. Okay, so the last case study I want to offer is in medical domain. Here, we try to take CT images with artifacts caused by metal implants and not only remove the metal pieces, but more importantly, remove the streaking artifact. You can see it if you look closely, streaking artifacts caused by the metal implants. Okay. To solve this problem, the existing models would require paired data. Okay. Given that it's very, very difficult to acquire paired data. Most methods use synthetic data. In other words, they take images without a metal implant, plant some metal digitally, and then apply some model to create the streaking artifacts. Okay. So, all right, with the synthetic data, you can build end-to-end training systems, right? Typically with a GAN. Okay. However, when applied to clinical data, models trained on synthetic data generalize poorly, because in the real case, the synthesis process is not accurate. Okay. Therefore, the model actually didn't learn an accurate representation for the artifacts. Therefore, it cannot remove the artifacts properly. Okay. So instead, we want to use unpaired clinical data to facilitate artifacts removal. Okay. But we don't have paired data, so that's number one. But still, number two, we can actually make use of unpaired clinical data to construct a loss in order to make the reconstruct image look as artifacts free as possible. Okay, and this was published in a paper in the ICMLA transactions on medical imaging. Okay, so what's our idea? Our idea is we want to explicitly disentangle the artifact from the content in the latent space. So imagine there's a latent space where we have the content and artifact disentangled. So all the bones, tissues, lesions, they are in the content space. All the artifacts, shades, streaks, noise, they are in the artifact space. Okay. If we could do this, then with the proper decoder, we can create an image without a metal piece and without the artifacts. Okay. All right. So to accomplish that, we construct the artifact disentanglement network. Okay. It's actually quite comprehensive. So I will explain in fairly good detail. Okay. Basically, if you look carefully, we have one image with artifact and then another image without artifact. They are not paired. Okay. They don't correspond to the same patient or structure. Okay. However, with the two of them, we can construct a number of output. And on these outputs, we can impose loss functions in order to allow us to disentangle artifacts from the content. All right. So if we, let's look at the first pass. So this is from an image with artifact. We have an encoder-decoder pair. Hopefully we reduce the artifact, right? And then we can compare this artifact reduced version with an image without the artifact. Notice this is Y, and Y is not a pair of X. We just need to compare these two to make sure that this artifact reduced image looks as much like the artifact-free image as possible. Okay, so that's the first pass. The second pass is because we try to disentangle the artifacts. So we have an artifact encoder. So we can take the artifact encoder and the content encoder and apply to another image without artifact, right? And thus create an artifact transferred image. We transfer the artifact of X to Y. And then we can compute an adversarial loss such that this artifact transferred image should look like an image with the artifact as much as possible. So that's the second pass. The third pass is, now that we disentangled the content and artifact, right? We can reconstruct a this image again, right? And then we can measure the difference between this self-reconstructed image and the input image. And we want to minimize the reconstruction loss. we use L1. Okay, that's not the end of it. We can take the Y without artifact, go through content encoder decoder, and do a self reconstruction. And we can reconstruct a new Y. And we want to make sure this new Y is as similar to the input Y as much as possible. Okay. There's more. Okay. So now that we have the artifact image and artifact free image for each one, okay, then we want to make sure that the artifact between these two images is consistent. Okay, there's more. Okay, and then we can start with X, right? Take the artifact, start with Y, take the content encoder, and we can transfer the artifact to Y, and then we reduce the artifact again, and we want to make sure this version is as similar to the starting Y as much as possible. Okay, so now we have considered all the scenarios and incorporated all the loss functions, right? So let's look at the quantitative results. First, these are just numbers by supervised scheme. Okay, you have to keep in mind these supervised schemes are trained using synthetic data. And this is the unsupervised scheme by us. And you can see that by PSNR SLM, we actually can do better than them. And that's actually not surprising for the reasons I already mentioned, because these synthetic data are not perfect, okay? All right, so, so that's the quantitative result. For qualitative results on clinical data, remember we have clinical data. So, so ground truth, we don't have it, right? This is real data, okay? This is the artifact image. And then you can, these are various schemes for supervised learning. And these are various schemes for unsupervised learning. Notice CycleGAN is also one of them, okay? But our scheme is more than CycleGAN. Remember, we have 5 to 6 loss functions in there to account for all the scenarios. So if you compare all these schemes, you can see that our method generates the sharpest image. Okay, these schemes tend to generate a blurred image. They don't look as sharp as the original image. And some of these schemes, they look sharp, but they also look noisy. Or they don't, like CycleGAN, you can still see the streaking artifacts, okay? So through both quantitative and qualitative evaluation, we have verified that our unsupervised scheme can produce excellent results for metal artifact removal. Okay, so I've gone through 5, 6 case studies to show how we can actually solve this problem of learning with unpaired data. So let me offer some concluding remarks. First, as I have shown, learning with unpaired data can greatly reduce the effort in collecting data and actually achieve good performance, okay? Typically, you can consider use cycle consistency to address this type of problem. However, if you can incorporate some level of explicit disentanglement of the compounding components, you can do better. You can improve the performance over just using cycle consistency alone. so far, from machine translation to image captioning, the performance of unpaired method is still lower than fully supervised method. Okay, but machine translation and image captioning are applications where it's possible, even though with the high cost, to have annotated data. In other cases where annotated data is impossible or nearly impossible to obtain, the performance of unpaired methods are better than supervised methods using synthetic data. Okay. So what are the open issues and possible future directions? Number one, we can consider combine learning with unpaired data and small paired data to achieve better performance. This was actually attempted in machine translation. Remember the first example I described today? Okay, so when you also have some small amount of paired data, you can consider semi-supervised learning, or you can use the small paired data for fine tuning, okay, to achieve higher performance. There may be other better ways of doing that, okay? Second, we can go beyond text and image modalities and consider other modalities or other domains, right? For example, if we want to generate multimedia videos with sound and video, then there's an issue of transferring the style. We need to match the style between the audio and the video, right? So that's one scenario where we can consider unpaired data. Okay. Another area that my group has been working on recently is sentiment transfer. In other words, we want to transfer the sentiment of image to another image, or transfer the sentiment of video to some audio. Okay. So it's very difficult to acquire paired data, but I think it's possible to do it with learning using unpaired data. Okay. Finally, I want to acknowledge two of my students, Yang Fen and Hao Fu Liao, who helped me with this presentation. They also contributed to two of the papers that I presented today. Yang is with Google Cloud now, and Hao Fu is with AWS. So that's all I have today. Thank you for your attention. And I think we have a good amount of time for questions.
Thank you. And thank Professor Luo for the great talk. Any questions? You also can put in the Q&A or put in the chat from the audience. Yeah, actually, I have one question, Professor Luo.
Okay. Mm-hmm.
Yeah, I know you talk about this in with examples of images, right? So I mean, it's very understandable for kind of pairs or unpairs. Is any kind of more scientific domain? Can you have this kind of pair issues?
Oh, that's a good question. So far we looked at language problems, vision problems.
Yeah.
By scientific, you mean like gene sequence and stuff like
yeah,
that?
something like that. Yeah, I mean more scientific applications. A lot.
Right.
Yeah.
Yeah, that's a good question. We haven't looked at that yet, although it's possible. I guess but I think it takes some thinking, right? It would be nice, this DNA or protein unfolding stuff, which is a big headline today, right? I don't know enough about the problem itself to like contemplate how we might do it with unpaired data, but it would be interesting to explore those directions. Yeah.
Also, I'm thinking another is kind of drug discovery, right? Or drug actions, right? So that could be very interesting to see how these algorithms or methods apply to drug, right? I guess.
Drug discovery and drug
Interactions, right? Something.
that would be those are fascinating domains for this type of machine learning problems. I think there is a question in the chat window.
Oh yeah, Q&A, yeah.
Okay, in most of the papers you use, how do you solve the convergence? Okay, that's a good question. Actually, GAN is as much as science as art. I think I can't say much about that. I think in most cases, experience is very important to work with GANs because their convergence is a problem, right? So some of my students are more seasoned than others. They know how to eventually make it work. But for newcomers, it's a challenge. I wish I can give you a good answer, but there are some tricks. I think if you look in the literature, there are some tricks that can help you deal with this, vanishing problems and whatever in a convergence of GANs.
Okay, thanks, Professor Luo. And any other question from audience? Oh yeah, another one.
Okay.
Thanks for the great talk. Can these tactics be useful for other type of denoising apart from the dehazing?
Certainly, yes. Denoising, yes. Low light condition, yes. We didn't do those because I think dehazing is a harder problem than those, at least from the point of collecting data. Like I said, noisy or non-noisy, you can use good camera, bad camera. You can manipulate with the exposure settings to get low light versus proper light, right? It takes some effort, but it's doable. But dehazing, usually you don't have real pairs, unless you really have the patience and the perseverance to go to the same location under different weather condition to collect data. The short answer to your question is for denoising, low light, absolutely. Third question, can your approach be used to generate fake image? I would say so as well. Again, we don't need pairs, right? So you just need some input images and then some output images. They are not pairs, but you can use this framework to generate realistic fake images. For example, we've done some work for virtual makeup, right? You wanna, so we can have, we don't have pair data, but then you have images with makeup and images without makeup, and then you can use, you can construct a scheme for learning or training with unpaired data.
Yeah, another one. Yeah, I have to think about time.
Okay.
Is your code available, or do you have a plan to publish the code?
So good question. I think our code is available. I can't say for all of them. I think for the Feng Yang's code is available in GitHub. Hao Fu's code is available in GitHub. The dehazing one, I'm not sure, because that student, left a while ago. So, but Yang and Hao just graduated early this year, so they did a good job on open source. Yeah, I can tell you a story which is beyond me. So Hao Fu put his code on the internet, of course his paper, and someone, I don't want to name the name or country, actually took the paper and code and wrote up a patent application and tried to patent the same technology in an outside US. And that was really, I mean, that was a compliment in some sense, but was really beyond me. Oh, there's another question.
Yeah,
Oh,
there's another. Maybe
okay.
just choose the last one because that's close to.
Yeah, I think the timing is perfect. I try to finish it right now. Okay, at the beginning of the you said better than the. The answer would be yes and no. I think you can try to create better data to improve these learning tasks, but it's risky, right? So when you artificially create data, you already use your human knowledge. If your human knowledge or human domain knowledge is complete, then do it, right? But we cannot say that all the time. So when you artificially try to create better data, you run the risk of incorporating your own bias consciously or subconsciously into the data, and therefore pass the bias onto your algorithm, which is dangerous. Okay, that would be my answer. So I guess, as the Jean said, we should stop here.
We should stop here. Okay. Let's thanks again for Professor Luo's good talk, and hope you enjoy this keynote.